Good morning, dear students.
Good morning.
Okay. Sorry, there was some meeting ID confusion. So I had to post another ID. Okay. So I formally welcome you all to the chemistry second year classes of mine. I think chemistry other part is done already for you, right? Did you get Sandeep sir class for this week?
Saturday. Yes.
Okay. That's fine. See, in my portions, the ionic equilibrium and the states of matter are the two important portions which are remaining from first year PUC that we'll take up in the due course. Let's not worry about it. We'll start a second year chapter straight away to start with. Okay. As you know, there is a physical, organic, inorganic. In second year PUC, the volume of organic slightly overweighs the remaining two sub branches. That is physical and inorganic. So next is physical, and then inorganic portions. Okay, that's how it's said. Now we'll take up one of the chapter, an important chapter under physical chemistry. That is solid state. You have solid state and solutions, chemical kinetics, electrochemistry, surface chemistry. So these are the physical chemistry chapters. So I would be doing all these physical chemistry chapters. Apart from that, two inorganic chapters, that is D and F block and coordination compounds. So these 7 chapters I okay for second year, right? We shall proceed with the solid state. So the moment when I say solid state, we will be also thinking of remaining two states of matter, liquid and the gaseous state. Did we have? Of course, I have not discussed, but the chapter is completed for you. Which chapter had liquid and gaseous state concepts discussed? Which was the chapter? You didn't study liquid and gaseous state in first year?
So states of matter.
States of matter. And also in physics, kinetic theory of gases, all those things you studied. So all those gas laws, kinetic theory of gases, and little thing about liquid state, that is viscosity and the surface tension, vapor pressure, these kind of things we have studied. There, in states of matter, first year PUC, we didn't study solid state because the entire chapter now in second year PUC is dedicated for this solid state. Like we are going to cover some fundamentals of solid state. Later, this branch of science will become crystallography. So in your higher levels, if you study chemistry, it becomes crystallography. Okay. Fine. What do we do in this entire chapter? So in a nutshell, if I have to give what is the content of this solid state, first we'll start with some classification and differences. After that, importantly, the arrangement of particles in solid, and related to this, so many different terminologies we are going to get. And at the end, properties of solids, be it electrical property or magnetic property, such kind of properties. So this is in a nutshell. Okay. So we'll proceed with the contents now. Okay. Oh. Yeah. So when I say the solid state, we shall just revise once the 3 states of matter under normal conditions of temperature and pressure. There is one more state of matter under extreme condition of temperature, which is the other state apart from solid, liquid, gaseous state? Plasma. So plasma is what actually? What is it made of? Plasma is made of what? You don't know what is plasma. So plasma is actually made of ionized particles. So at very extreme conditions, the matter will be in the ionized form. So plasma is nothing but ionized matter. So under normal condition, it is only 3 states. Fine, we shall take solid, liquid, and the gaseous state. When it comes to the solid state, some of the characteristics which make or which define the matter in solid state. Coming to the definite volume and shape. So matter in solid state will have definite volume and definite shape also. Particles will be very closely spaced. Okay, so there will be no much gap between the particles. So therefore, the interparticle distance will be very, very less. When I say particle here, a particle is a general term. It may represent an atom in a solid, or a molecule, or an ion, which is the solid is made of. For example, if you take sodium chloride, is made of ions. If you take solid iodine, it is made of iodine molecules. So like that, solid can be made of ions, molecules, or atoms. All put together, it is termed now as particle. Okay. So in solid state, particles will be very close. Interparticle distance will be the lowest. And interparticle interaction or force of attraction between the different molecules will be highest. So maximum interparticle interaction. Next is thermal energy. The low thermal energy. Now, what is thermal energy? Anybody knows about this thermal energy? See, the total heat content, we have another term to define that as enthalpy. Now, this is thermal energy. What is thermal energy? You know?
So heat energy.
There is a heat energy is heat content is nothing but enthalpy. What is thermal energy?
The energy is connected to the motion of particles in solid.
Okay. If energy is connected to the motion, it is actually called kinetic energy, right? Then what is thermal energy? Kinetic energy is the energy that is associated with the movement of the particles.
Sir, it is produced when rising temperature.
Come again?
It is produced when rising temperature.
Rise in temperature. When temperature rises, kinetic energy increases.
Sir, the internal energy of a body.
Internal energy is internal. Internal energy will be internal energy only, no?
Collision of particles, sir.
Collision of particles. Okay. So if I leave, all concepts will come into this now. Whatever we study under reactions. Okay.
So the energy produced when the heat of the body increases so that the atoms and molecules split and collide.
That is overall energy. Correct. So thermal energy specifies.
So within the substance.
Pardon me?
So what Shashank said was right, but he must have within the substance.
Your voice is not clearly audible for me, Krishna.
That's fine, sir.
Now listen to me. See, kinetic energy refers to a molecule. How exactly with increase in temperature, the moment increases or the kinetic energy varies. So kinetic energy for a particular molecule. But when you take the entire bulk of the matter in any state, the kinetic energy is referred as thermal energy. So all different movements is together under thermal energy. Okay. So with respect to a molecule or a mole can be kinetic energy. With respect to every entire bulk of the matter would be called the thermal energy. So in that way, it is associated with the kinetic energy itself. Now, when molecules in the solid state are arrested, they don't move, their thermal energy is low, but still they will have vibrational energy and possibly rotational energy. These kind of some energies will be there, but not like liquid and gaseous state, where molecules also will have translational energy of movement. So this is therefore particles in solid state will have low thermal energy. and least entropy. So what do you mean by entropy? Entropy, you don't know.
Sir,
What do you mean by
disorder.
disorder? So disorder is lowest in solid state because the particles are neatly arranged. So that's the reason. So these are all some of the characteristics. Apart from that, the important striking property of solids is they are incompressible or rigid. So you can't compress any solid of any mass, right? So it will have definite volume, definite shape. That's the reason they say. So they're characterized by rigidity or incompressibility. So the other state of matter which has almost different properties, quite opposite to solid state, or characteristics are quite opposite, is gaseous state. Here, no definite shape, no definite volume. Okay, it will take the shape of the container, and particles are quite away from each other. When compared to solid state, they are quite far away from each other. So therefore, when distance between the particles increase, the interactive force, intermolecular force decreases. So they will have all sorts of kinetic energies associated. Their total thermal energy is very high, and the disorder will be maximum. So therefore, they possess highest entropy. They are indefinitely compressible and expanded. So you can take 1 mole of gas and keep it into any container. The entire space will be occupied. Similarly, you take 10 liters of gas and apply pressure, it can be indefinitely compressed also. So therefore, they have high compressibility factor. Now the liquid state of matter will have moderate properties. So definite volume is there, but no shape. Because of definite volume, they are also incompressible, but not rigid. Okay, they are incompressible, but no shape because they take the shape of the container like gaseous state. Moderate interparticle distance and interparticle interaction when compared to solid state and gaseous state. There is little more thermal energy than solid state and more entropy than solid state. They're incompressible but not rigid as I said. Okay, so these are some of the characteristics which we know. I think thermal energy is one which you need to add into your knowledge of these characteristics. Okay, so rest everything we know so far. So these are some of the major characteristics and also differences between solid, liquid, gaseous state of matter. Okay, now our emphasis is more on solids. To start with classification of solids. Generally, most of the chapters start with classification. Classification always helps us study the subject better, understand the things better, and also know the properties in a better way. So classification always helps the further exploration. So therefore, always classification is important. Coming to classification, see solids you would have seen. So if you see some of the solids, they will be having a kind of roughness. Okay, some of the solids will have smoothness. Even if they are taken in the finely powdered state, the powder will be very, very, very fine in one case. In another case, it will be kind of crystalline, okay, rough. You want previous slide, Dhanushri? 1 second. She wants. Yeah.
So should we take down this or only solid parts?
Your voice is not somehow clear, man. I couldn't get what
Sir,
you.
he's asking if we should take down all like solids, liquids, gas, or only solids. If we take down, it's enough.
No, differences I have given. Differences when I say you have to take all these things. No? Huh? Okay. Krishna, you need to be, I don't know, either you are very close or very far. Voice is not clear. No. Shall I proceed now?
Yes, sir.
Okay. So based on physical state of solid, there are 2 types here: crystalline solid, amorphous solid. Okay. So the crystalline solid characteristics will be: crystalline solids, they possess definite geometry. and that geometry is long range. Okay, they possess definite geometry, and the geometry is long range. So what do you mean by definite geometry? We have already told the solids possess definite shape. So if I say a crystalline solid possesses definite geometry, there is already shape which we have told as solid, be it crystalline or amorphous, there is definite shape. Then how exactly this definite geometry of crystalline solid is different from the definite shape? Anybody? What did you understand by this term?
An irregular shape.
Huh? What is it?
The shape can be of any type, but geometry means one proper symmetrical thing.
Proper symmetrical thing. Okay. Next.
For a long time, it possesses the perfect geometry.
For
Uniform.
okay. Here regular shape and irregular shape. Regular shape and irregular shape is shape only, no? How it is geometry?
So uniform arrangement results in crystalline
Okay.
solids. And
Okay.
maybe uneven arrangement
Okay.
can be.
See, when I say geometry, geometry refers to the molecular or particle arrangement inside. It is microscopic. Geometry always means how particles of the solid are arranged. So that is geometry. Now, whatever is the geometry of the molecule, for external appearance, there is a shape. Okay, that is the shape. Shape is for the bulk. Geometry is for molecules. Okay, so now you would have taken some amorphous solid, say some calcium carbonate powder, and some sodium chloride. So there is two heaps, and they have their own shapes, definite shape. But you go deep into it and see how particles are arranged. That gives the geometry. The arrangement of particles inside the crystalline solid is definite. There is definitive arrangement of particles which is maintained throughout the solid constant. The arrangement is long range in the entire solid. Okay, so the particles are neatly arranged in a definite manner, and the entire arrangement is for the entire solid. That is what we mean by saying long range. And these crystalline solids will have sharp melting point. You take a solid, heat it at a particular high temperature, the solid converts to liquid. That's why they are also called true solids. Okay, crystalline solids are called true solids. Now, geometry is long range. For the entire solid, the same geometry is same. You break the solid, crystalline solid, into small pieces. The small pieces also will have same arrangement. There is no different arrangement because it is long range. Again, another striking difference between crystalline and amorphous would be this property that is called anisotropy. As a property, it is called anisotropy. They are anisotropic. Crystalline solids are said to be anisotropic. What do you mean by that? You take a crystalline solid, for example, all metals, or for example, these ionic solids like cesium chloride or sodium chloride, they're all crystalline solids. You take sodium chloride block and measure the values of density, refractive index, conductivity values. So it will be same in all, it will be different in all the directions. Okay, so you are going to measure density in a particular direction. The value of density found out in that direction will be different from the another direction. It will be different from another direction. So from direction to direction of measurement, these values of physical properties such as density, refractive index, conductivity differ. So it depends on direction of measurement. That is said to be anisotropy. We can take some examples like metals. All metals are crystalline. Ionic solids like sodium chloride, zinc sulfide, they're all crystalline. Some of these molecular solids like solid iodine, ice, dry ice, they are also crystalline. Okay. Exactly. Physical properties such as density, refractive index, conductivity values are not same in all direction. That's correct. Okay, that is what is crystalline solid. So these are some of the properties that is characterized by this crystalline solid. We'll take up amorphous. Obviously, under each point there is a difference. We'll take up one by one. Amorphous solids possess no definite geometry, and if at all, if some arrangement is there over a small region, the arrangement will be specific. That's why it is called short range geometry. The same geometry is not extended throughout. The very next neighborhood will have a different geometry.
Excuse me, sir.
Like, tell me.
Sir, are all crystalline solids lustrous, sir?
To be frank, this valid point can be taken. Lustrous kind of shining surface will be there. But when I say that, what about the metals like iron? There is little lustrousness, and that cannot be properly exhibited at all. By and large, we can say they shine in light. They are lustrous. Amorphous are not so. Okay. And when I say amorphous are not so, in some cases like a glass, there is a shiningness that can be there on the surface slightly. So this property is not very important different. By and large, we can say that property correctly. Okay, right.
Yes, sir.
Yeah, I was about to give an analogy for this definite geometry and not definite geometry for crystalline and amorphous. You take a classroom, there are say about some 25 benches, and students come and arrange. In each bench, four students specifically get accommodated. So entire classroom has four students in each bench. So there is a definite geometry. That geometry is extended throughout the classroom. It's a long range. So that is crystalline. Okay. Now, in another case, another classroom, 25 benches, students come and rush in, and first bench has 5 students. The very next bench has 3 students. Then next bench has 7 students. They're all friends. They want to sit there. So that kind of disorder is more. There is a arrangement in each bench. Each bench has its own specific arrangement. The very next bench has different arrangement. So that's why it is called short range geometry. So that kind of no definite geometry throughout is what is amorphous solid. So similarly here, in case of amorphous solid, you take the solids and start heating. Slowly, the process of melting starts. That means over a range of temperature, melting takes place. Not at a particular temperature, suddenly the melting starts. So at a particular region, slowly the solid converts to liquid and converts to liquid. So like that, over a range of temperature, entire mass converts to liquid. That's it. So there is no sharp melting point, meaning they melt over the range of temperature. For example, glass. Glass is amorphous solid. You take glass and start heating. Slowly it softens first and then converts to liquid. Okay. So they are pseudo solids, especially they are also called in case of glass and all super cool liquids like. So these amorphous solids are pseudo solids, or in some cases they are also called super cool liquids. So glass is a super cool liquid. Liquid, when I refer any substance as a liquid, it has to have a flow. Correct? So if I throw a liquid, a liquid moves. So different liquids will have different viscosity. The rate at which they move would be different, but there should be movement. So if I say glass is a super cool liquid, it has to move, but glass doesn't move. See, instantly in a day or a month or a few years, you may not observe. You go to any old building, which is old of the order of 100 years or 200 years like that. And you go and check the windows glass panes, 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 window glass panes. There will be thickness at the bottom of the pane, and the top surface will be little thin. So over that period of time, there will be some kind of movement that would happen. So that is witnessed by this difference in thickness in the old building windows glass panes. So thickness at the bottom will be more, and the thickness at the surface of the window pane will be thin. So therefore, that also shows that there is kind of movement there. But however, it takes place very slowly because of very high viscosity. So that's why they are pseudo solids or super cool liquids. Okay, right. Third one, when you break a amorphous solid, the small pieces obtained will all have different geometries, obviously, no. So because the geometry is not long range, it is short range. And another striking difference with the crystalline solid is these amorphous solids are said to be isotropic, and the property is called isotropy, and amorphous solids are isotropic. What do you mean by that? The physical properties such as density, refractive index, conductivity measurements will all be same in all the directions. Okay, so it doesn't depend on the direction of measure. That's the meaning of it. So some of the examples: glass, wood, plastic, and especially carbonate salts. Okay, most of the salts are examples of crystalline, and some of the carbonate and bicarbonate salts are amorphous. You should know this. Now, one question at the end of this discussion remains is, how come definite arrangement in case of crystalline solid results in anisotropy, and how come no definite arrangement of particles in amorphous solid results in isotropy? Correct, no? So why amorphous are isotropic? Why crystalline solids are anisotropic? So for that, we'll take this discussion. This particularly gives you clarity about how exactly
Excuse me, sir.
anisotropy created. Tell me.
Can I go for present?
Yeah. Go.
Sir,
Yeah, tell me.
so the fourth point in amorphous solids, sir, values is different in different directions. It's
Correct.
the opposite, no, sir.
Exactly.
It's not different in different directions.
Obviously, in each direction, the values are different, means it is different in different directions. Depends on direction of measure.
Because even for anisotropic, the
In
same
both
one
the
is
cases, it's
Yes,
sir.
so for isotropy, you're telling, okay. Values
Yes,
are
sir.
different in different. Oh, sorry, it has been printed as values are same in all or same in different direction is correct. It should be. It should not be different in different direction. It should be same in different direction. Sorry, thank you. Thanks for pointing it out. So values are same in different direction for amorphous. It's different in different direction for crystalline. Okay, I would change that one later, but now you change it. Values are same in all directions.
Yes.
Yeah, thank you. Yeah, we'll take up next. Shall I proceed now?
Yes, sir.
Yeah. Now, what is that we are going to see? So, how come isotropy for amorphous solid and isotropy for crystalline solid, though there is a definite geometry? Let's see. I have taken these two pictures here. You have to tell me left hand and right hand. Picture 1 and picture 2, better say that. So, in the picture 1, you can see the particle arrangement. Each dot or circle indicate the particle composition in the solid. Okay. On the right hand side, there is kind of arrangement. So which would represent crystalline?
Left hand.
Left hand. Okay. So that represents the crystalline, obviously. So there is definite arrangement. For example, if you take this as sodium chloride, there is sodium ion and Cl minus ion. Sodium ion is relatively smaller when compared to the Cl minus ion. Okay. So the Cl minus ion will be little larger. Okay. So let's say this is circle. You can see any direction. For example, here it is marked A to B. In A to B direction, all Na plus, smaller Na plus are placed. And if you take C to D direction, you can see Cl minus, alternatively Na plus, Cl minus, Na plus. Or you can take one more direction, this direction. In this direction, you can see only Cl minus have been kept there. That is, larger particles are there. So because of definite geometry, how exactly particles are arranged in NaCl? Na plus, Cl minus. A very alternative position, the alternative ion or opposite ions will be placed. Because of this definite geometry, in any one particular direction, the mass distributed will be different when compared to the other. So along CD, there is larger, smaller, larger, small. Along AB, only smaller. Along another direction which I have marked there, only larger particles are there. So when I say that, because of this definite geometry, mass distribution is different in different direction. So when you measure density, density is mass by volume. Density also should be different in different direction. That's as simple as. So when density is different, all related properties also will be different in different directions. Okay. So thus, the definite geometry is the root cause of anisotropy in crystalline solids. Okay. So when it comes to amorphous solid, you can see the particles are completely haphazardous. There is a lot of chaos there. And arrangement is not definite, but there is one thing which is common. What is that? Entropy. All across, disorder or entropy is same. Am I right? Entropy is constant all across. You measure any direction, there is disorder which is constant, not geometry. So as a result, you measure the mass distributed in any direction, by and large it remains the same. Hence, density and all other properties also will have same values in all the directions. So thus, having no geometry, definite geometry, results isotropy. Okay. So what is constant across the amorphous solid? It is the disorder is constant or entropy is constant there. So because of which density, conductivity measurements, and refractive index, all such properties will be having same values in all the directions. This results in isotropy. Okay. So hope the concept is clear. Let me give one more diagram here. Okay. This is just an anisotropy is due to different arrangement of particles in different directions. Isotropy is due to same disorder, the word disorder or entropy of particles in different directions. You can take this diagram also. On the left hand side, you can see anisotropy due to perfect arrangement. In any direction, there is one particular particle that you find. So you can see there is disorder, a lot of disorder on the other diagram. So because of which the isotropy, that is similar properties, will be found in all the directions. Hope this also adds to the clarity. Hope it's clear. So shall I proceed now?
So 1 minute.
Yeah, come on. Shall I proceed now?
1 minute, sir. Yes, sir.
Okay. Now tell me, if I say sodium chloride, it can be an example of sodium chloride,
Anisotropy.
anisotrope, and it is amorphous or crystalline.
Crystalline.
Okay. Metals like copper,
Crystalline.
crystalline. Glass,
Amorphous.
wood, amorphous. Calcium metal,
Sir, amorphous.
calcium metal. Calcium metal is crystalline. Calcium carbonate,
Amorphous.
amorphous. Calcium chloride,
Amorphous.
no. Calcium chloride. Chlorides are crystalline salts. Like that. So that's why. Like magnesium metal,
Crystalline.
magnesium carbonate,
Amorphous.
sodium bicarbonate,
Amorphous.
sodium metal,
Crystalline.
like that. Okay, so that fine. We'll take up further. Now we'll take up classification of crystalline solid, particularly based on the composition. Crystalline solids are we can get a wide variety of crystalline solids as examples. Okay, so based on composition, that is, what is it made of? There are 4 types of crystalline solids. First one, ionic crystals. Very easy to say. Ionic crystals are made of what particles?
Ions.
Ion. If ionic crystals are made of ionic particles, covalent crystals are made of?
Covalent bonds.
So I always guess this answer. That's why I intentionally asked. So ionic crystals are made of ions. Covalent crystals are made of
Molecules.
covalent bonds. Only bonds will be there. No. Okay. Molecules, if it is there, if at all, if molecule is there as solids, then it becomes molecular solid, not covalent crystals. Okay. So this will confuse you for the reason that till now in organic chemistry, we have studied organic molecules as covalent molecules because they have covalent bonds. But when those organic substances containing organic molecules, when they solidify, they will be made of molecules. That means entire solid will have molecules in it. Therefore, they become molecular solid. If entire solid has ions, if ions make the solid, then it is ionic crystal. Similarly, what should be the covalent crystal?
Atoms.
Atoms. For example, diamond. Diamond is an example of covalent crystal. What is it made of? Carbon atoms. Only carbon atoms are. Okay, so no confusion. There shouldn't be confusion between organic covalent molecules and covalent crystals. Covalent crystals are solids which are made of atoms. That is important. So these covalent crystals will have generally kind of 3-dimensional bonding and all in the solid state. That's why they're also called network solids. Coming to ionic crystals, some characteristics. Ionic crystals are made of opposite ions. No issue. And what is the force that is responsible for holding them together, or which force will stabilize them in solid state?
Electrostatic force.
It is the ionic bond, which is electrostatic in nature. Why do we say ionic bond is electrostatic in nature? Because it exists between 2 oppositely charged ions, whereas covalent bond is not electrostatic. It is formed by mutual sharing up of electron. It doesn't exist between plus and minus ion. So that's why ionic bond is electrostatic. So held by electrostatic force, that is ion. They are generally characterized by hardness, brittleness. What is brittleness? So
They
when
will
you
break when force is applied.
exactly, they break down, or rather when they break, they become powder. That is brittleness. Okay, so glass is said to be brittleness. Like that. That brittleness means apply the external force, the substance breaks down into powder. Okay, so they break down easily. That is brittle. and possess high melting and boiling point is what is one thing. Okay, right. Next, they are good electrical conductors. How come they are good electrical conductors? Is there electrons present in ionic crystals? No. Metals conduct electric current. In case of metals, electric current conducts because of electron migration. Electrons are responsible for conduction in metals. Whereas in ionic crystals, ions are responsible. Ions are the charged species which can carry the electric current in the solution phase. So they conduct electric current in solution phase and in molten state. When it is melted, the ions set free. When it is dissolved, ions become free and thus they conduct electric current. How about conduction of electric current by ionic crystals in solid state? Will it conduct or not?
No, sir.
It will say in molten state.
No, in solid state.
No, sir.
It won't.
No, that's because ions are absent or present.
Present.
Because of electrostatic force, they will be tightly bounded.
Exactly. So that means ions are present still, but they're not free. That's all. So in solid state, ions are there, but they're not free. They're strongly held by these ionic interactions. Therefore, they will not move. They'll not conduct. So that's it. So not in solid state. So some of the examples you can see. We'll take up covalent crystals. So some of the points, they are made of atoms in the solid state. That means atoms only repeat to produce the entire solid. Between these atoms, the force that is responsible is the covalent bond. They are held by covalent bonds. Here, this point I just want to correct. This covalent crystals, they will have very high, okay, very high melting and boiling point. Moderate is not there. Okay. So ionic crystals have high melting and boiling points. Covalent crystals have very high melting and boiling points. Again, don't get confused with covalent molecule, that is organic molecules. Covalent crystals means immediately you should get into mind, that is graphite, diamond, this kind of examples. Their melting and boiling points will be of the order of 2000 to 3000 respectively. So 2000 to 3000 degrees centigrade. So in that way, their melting and boiling points will be too high. Yes. They are non-conductors of electric current in general, but graphite is an exception. Graphite, though it is covalent crystal, it conducts electric current. Have you studied the structure of graphite and diamond in P block elements first year? That was under reduced syllabus. Probably wouldn't have studied, right? In P block, did you study structure of diamond, graphite, all those things?
Yes, sir.
Oh, is it? So why do we say graphite is a conductor? What makes graphite to be conductor and not diamond?
Sir, due to its arrangement, it's very far away from its basic molecule. There is a gap.
No. Arrangement only gives the structure, not the electrical property.
Sir, and is graphite Sp2 hybridized? Is that?
Okay. So if it is Sp2 hybridized, how come it can be conductor?
So there's an electron.
See, carbon has 4 valence electrons.
Yes, sir.
But carbon in graphite undergoes Sp2 hybridization, meaning only 3 hybrid orbitals will be produced. They will be involved in bonding, and one orbital which is not involved in hybridization will contain a free electron. Though it undergoes sidewise overlapping to form a pi bond, but those electrons of pi bond in graphite can be subjected for movement when external potential is applied. So that's why graphite has free electrons which can contribute for the conduction. That free electron is because it is not bonded. That is because again carbon is Sp2 hybridized, whereas in graphite, in diamond, carbon atom is Sp3 hybridized, meaning there are 4 hybrid orbitals of Sp3, and all the 4 hybrid orbitals bond with neighboring carbon atom, and none of the electrons are free. That's why diamond is not a good conductor. Anyhow, so generally when we speak, they are non-conductors of electric current, is true. Okay, by and large. So examples, you can take diamond, graphite, quartz, silicon, carbide, SiC. boron carbide, Bc. This
What is quartz now?
SiO2, silicon.
So how can we take graphite as an example?
It contains only carbon. Because it is made up of atoms, it is a covalent crystal. That is what your concern?
No, sir, it conducts electricity. No?
No, that's why when we give general characteristics, specific case can be excused. Okay, but it is a covalent crystal. One of the property it doesn't follow, that's all. If you don't take graphite, where do you belong the graphite? It doesn't belong to any other category, because it is made up of atoms and held by covalent bonds. Importantly, it is covalent crystal, but that one property is not followed because of it's an excuse. Okay, whatever we are taking here are general differences. In every case, it need not be the same. By and large, these differences hold good for the entire bulk of the examples. Okay, shall I proceed now?
Yes.
So just 1 second.
Yeah, come on.
Done, sir.
Okay. Next, we'll take up molecular crystals. There is no confusion here, as the name itself suggests. Molecular crystals are made of molecules. Only confusion is ionic crystals are made of ions. Covalent crystals, immediately we say covalent. No, covalent crystals are made of atoms. Molecular crystals are made of molecules. Then which force would stabilize them or hold them together in the solid state?
Van der Waals force of attraction.
Exactly. Between molecules, what do we expect is van der Waals forces, like dipole-dipole interaction, dipole-induced pole interaction, or induced pole-induced pole interaction. These kind of things, right? Now, under molecular crystals, as we know, they are made up of molecules, but there are 3 types again. Okay, so you can say they are made of molecules. And there are 3 types. So which are the 3 types? Number 1, non-polar molecular solids. That means they are made of non-polar molecules only. Non-polar molecules means there is no polarity, there is no charge. Can I take water as non-polar molecule?
No.
No. Can I take carbon dioxide as non-polar molecule?
Yes, sir.
Yes. Any molecule with dipole moment mu equal to 0 is non-polar. Am I right? Any molecule with mu not equal to 0, that means if the molecule has some value for mu, then the molecule is said to be polar. We have decided how to find dipole moment based on the structure and all in the chemical bonding chapter, correct? So this is how polar and non-polar is decided. So carbon dioxide is linear, its dipole moment get cancelled, mu becomes equal to 0, it is non-polar. Okay, so they are held by dispersive forces or London forces or induced pole interaction. Those induced pole interaction is nothing but London forces or dispersive forces there. Right? Any molecular solid will have this property common, soft and non-conductors, because they doesn't contain ions. They possess low melting and boiling points, all these molecular solids. So examples are important for the reason that these examples only will be given. So which among the following are polar molecular solids or non-polar or some kind of things? Okay. Dry ice. What is dry ice?
Solid carbon dioxide.
Solid carbon dioxide. So this dry ice, it immediately sublimes. Solid carbon dioxide sublimes to gaseous phase, and it gives thick white fumes. So that's the reason why on the stage shows and all this solid carbon dioxide will be used to indicate or induce some kind of foaming or foggy atmosphere, right? So anyhow, so dry ice is nothing but solid carbon dioxide, solid iodine, solid argon. Okay, there is one thing when it comes to an example of solid argon. Solid argon means what? Argon, noble gas. Helium, neon, argon, krypton, xenon, radon, they're all noble gases. When these noble gases are converted to solid, they become example for non-polar molecular solid. But noble gases are made of monoatoms, or they are made of molecules. Noble gases. They are made of atoms or molecules.
Atoms.
Atoms. When they are solidified, they solidify only as atoms only. That means solid argon is made up of atoms. So it should come under the example of covalent crystal, right? But it's been given under non-polar molecules. Because solid argon doesn't contain molecule, it contains atoms.
So sharing of electrons are not.
Okay. Why sharing up of electron is not there? Because they can't form bond. Their octet is complete. So they will not form bond and exist as molecules. Yet solid argon or solid krypton can be considered as non-polar molecular solid for the reason that they don't have covalent bond between the atoms. One argon in solid state can be held by another argon by dispersive forces only. There is no covalent bond. And the remaining properties of solid argon also matches with non-polar molecular solid. It is non-conductor, possesses low melting boiling point, all this. And there is van der Waals forces in it. So as a result, though solid argon contains atoms, it is more like non-polar molecular solid with respect to the properties. So therefore, it is more like molecular solid. Next example, the polar molecular solids. Polar molecular solids are made of polar molecules, that's all. And between two polar molecules, there can be dipole-dipole interactions. Okay. And again, as I told you, soft and non-conductors, that is a common property. They possess low melting and boiling points. But the thing is, dipole-dipole interactions are greater in magnitude when compared to the dispersive forces. As a result, compared to non-polar molecular solid, melting and boiling point will be slightly higher due to little more stronger interactions. Like solid sulfur dioxide, solid HCl, solid HI, they're all examples of polar molecular solids. The other category is hydrogen bonded molecular solids. Hydrogen bonded molecular solid are also polar molecules for sure. If hydrogen bond has to be developed between two molecules, the molecule must be basically polar. Then you people have to tell me under what circumstances you develop hydrogen bond between molecules in substances.
Hydrogen bond.
Hydrogen
Bonding between ions.
No, the question is that itself. Under what conditions hydrogen bond develops? Is it just having hydrogen atom is enough, or any other condition?
Should be with the electronegative element.
Electronegative element like chlorine, bromine, and all.
Yes.
No, they are electronegative, but they're not as electronegative as three most electronegative elements. Fluorine,
Nitrogen, oxygen, fluorine.
So fluorine, oxygen, nitrogen, these three elements. Hydrogen bonding is observed in those substances where hydrogen is attached to either fluorine or nitrogen or oxygen, any one of these. For example, HCl. In HCl also hydrogen is attached to chlorine, which is electronegative, but there is no hydrogen bond because chlorine is not as electronegative as fluorine. So therefore, solid HCl can be an example of polar molecular solid, whereas solid HF becomes example of hydrogen bonded molecular solid. Okay. So held by hydrogen bonds, contain hydrogen attached to nitrogen or oxygen or fluorine. That's important. So soft and their liquids can be solids under normal conditions. Okay. So they are non-conductors. That's common. Ice, simply ice is that is water as solid. So solid ammonia, solid HF. Can solid alcohol, like ethyl alcohol, be an example of this particular category? Solid alcohol.
The carbon is there.
No.
Solid alcohol, ethyl alcohol, for example. What is the formula
No,
of
sir.
ethyl alcohol? Ethyl alcohol is C2H5OH. So now can you answer?
There is covalent bond.
No, pa.
So
Can there be hydrogen bond between two ethyl alcohol molecules? So when two ethyl alcohol molecules come closer, it always so happens that hydrogen can come between oxygen and oxygen. So when hydrogen atom comes between two electronegative atoms in the among the three atoms, that is nitrogen, oxygen, fluorine, there is always a hydrogen bond expected. So between ethyl alcohol molecules, there is hydrogen bond. Between water molecules, there is hydrogen bond. So if you take solid ethyl alcohol, can be an example of hydrogen bonded molecule. Okay. Okay. So these are the three different molecular crystals. Next, we'll take up the fourth one. Is it complete? Should I wait?
Yes, 1 minute.
Yeah,
It's
yeah,
complete.
right. Okay, shall I proceed?
Yes, sir.
The fourth one and the last one under molecular crystals is, crystalline solids is metallic crystals. Now, ionic crystals are made of ions. Covalent crystals are made of atoms. Molecular crystals are made of molecules. And metallic crystals are made of what? Come on, I say.
Metallic bonding.
Only bond can't be the composition, right? Bond can be there between any two entities. Bond only cannot make substance.
positive ions.
Metals contain positive ion.
Because there is free electrons.
As conductors.
Okay. So according to Nityashri, it is metal. So for example, if you take iron metal, there is iron cations. You mean?
Sir, I know there is free electrons, sir. I'm just guessing it can be positive ions.
Okay. Somebody else were saying something.
So they act as conductors.
So they act as conductor, correct? But what is their made of composition? Metallic crystals contain what metals are?
Fluid C model.
Fluid C model. Where have you studied, Vrinda?
College that.
It's done because solid state is completed.
No, sir, they haven't started. They are just completing ready syllabus.
She told us extra information.
No, this solid state is commenced already in college.
No, sir.
Okay, where have you studied then?
Chemical bonding, last part, ma'am did the metallic bond.
Yes.
Okay. Actually, that belongs to this chapter. That's why I didn't do that. Anyhow, we are going to give little more emphasis on this. That's the correct answer. We'll see that. Okay. We'll elaborate here. So when it comes to metallic crystals, so we may immediately tend to answer like this. Since ionic crystals are made of ions, metallic crystals are made of metals. It is a wrong statement. Metallic In metals only, what it is there, I'm asking, right? So metallic, so in some sections they answer like metallic crystals are made of metals. So it cannot be. So therefore, what is the scenario in metals actually? They are made of positive metal ions. There will be array of positive metal ions held by negative C of electrons. The negative C of electron will be one side, and this positive array of metal ions in the metal will be another side. There will be strong electrostatic force between those two. That force holds them together. That itself is called metallic bond. In the next slide, I'm going to elaborate what is this metallic bond and how exactly the theory proposes the concept, all those things. We'll just take the differences or characteristics here. Metals do possess high melting and boiling points. But among all the four crystalline solids, it is the covalent crystals which possess highest melting and boiling point. Okay. So if anybody says moderate or low, no, that's not correct, because they would have got confused with organic molecules there. So covalent crystals will have highest melting and boiling point, then it is metals, then this ionic crystals, then molecular. Okay. So high melting and boiling point. Conductors, there is a whole lot of properties which are unique and specific to metals, like conductors, lustrous nature, photoelectric effect, all those things will account just now. Some of the examples. So these are metallic crystals. So under crystalline solids, based on composition, ionic, covalent, molecular, metallic, this type. So examples under each category is important to remember. Now let us take up some discussion on metallic crystals.
So can you go to
Yeah. Okay.
Done, sir.
Okay. So I'll proceed. Next. So what are these metallic crystals? Metallic crystals are made of an array of long rows, array of positive metal ions submerged in sea of negative mobile electrons. How is this possible? This idea was given by a theory, that is electron sea model. It's also sometimes called electron gas theory. Okay, electron sea model proposed by Drew and Lorentz. They only have given this kind of concept to explain all the unique properties that metals possess. This metallic bond is also, in a way, is unique. Why? See, a bond which is formed between two oppositely charged ions is ionic. It is formed by donating electron and accepting electron completely. Whereas if two atoms come closer, and if they are not ready to donate electron to one another, then they share. Then it becomes a covalent bond. So a covalent bond is generally formed between two atoms of similar electronegativity and electron affinity. Okay. What about metals? Between two metal atoms, what kind of bond could be possible? Between two metal atoms, what kind of nature will be there? Both the metals will be ready to donate electron. Metals are electropositive. Between two electronegative atoms, there can be covalent bond. Between one electropositive and one electronegative atom, there can be ionic bond. Between two electropositive atoms, what kind of bond could be there? It is a metallic bond. Both are ready to donate. They are not ready to share or accept or what. So now you can see metals possess, any metal for that matter, they possess low ionization energy and they are characterized by a high electropositivity. These two factors makes the metals lose electron easily under any condition of temperature and pressure. Okay, you take any metal, they are having low ionization energy, so removal of electron is easy. They are characterized by high electropositivity. They are ready to donate electrons. So these two characteristics make them lose electron under any condition from their valence shell. If you take a particular metal, the valence shell electron would have been out of the control of nucleus. Like that, in a sample of metal, there will be billions, millions of atoms. From all the atoms, valence electrons would be out of the atom. If electrons are out of the atom, what remains in the solid is the array of metal ions. because metal atoms, after losing the valence electron, would become positive part. That positive part will make array of metal ions. All those electrons which are removed from the valence shells of different atoms will form a huge sea of electron. That huge sea of electron formed will submerge the array of positive ions called kernel of ions also. And there exists a strong electrostatic force of attraction between negative sea of electron and positive array of metal ions. That's called metallic bond. And the electrons in the sea, they are ready to move from one point to another point. And that's why metals possess some unique properties not seen in all other substances, for the reason that here the electrons which are there in the metallic bond are mobile, whereas in all other bonds, the electrons which are there present in the bond are not mobile. If electrons of the bond are moving, it is as good as breaking the bond. A covalent bond will have 2 electrons. As long as the 2 electrons are static, the bond is stable. If electrons of the covalent bond are moving, it simply means that it has been broken. Whereas here, the metallic bond has mobile electron. Altogether, concept is different. Okay. So valence electrons collectively form negative sea of electron, leaving positive array of metal ions, that is kernels. The negative sea of electrons submerge the positive array of metal ions. The imagination can be something similar to this. So after losing electrons from the valence shell, what the core remains is what is positive. See, all these positive array of metal ions are submerged with negative sea of electron. The negative sea of electron would be containing more electrons in case of D block elements, would be containing less number of electrons in case of S block elements. What could be the reason? In S block elements, valence electrons are very less. It is NS1, NS2. Whereas in D block elements, valence electrons means it is NS electrons and also N-1 D electrons. Both the electrons can be lost in case of D block. That's why the negative sea of electron will contain more electron density in case of D block elements, whereas less electron density in case of S block elements. So in that way, the metallic bond in case of D block element is stronger. The metallic bond in case of S block elements are weaker because of less number of electrons. And mercury is a liquid metal for the reason that metallic bond is too poor it is, though it is D block, because number of electrons contributed for metallic bond formation will be only 2 electrons. Apart from that, the size is too large, so that interatomic interactions will be poor. So that's why it exists as liquid. Okay. So the electrostatic force of attraction between the mobile electrons and fixed array of metal ions is called metallic. Already people are leaving. Still it is 9:15. You have to be till you have to wait for the class to complete. Okay. What time you have college classes?
Sir, at 10.
10. Okay. No, both are electrostatic in nature, Krishna. Both are electrostatic in nature. Ionic bond, metallic bond, both.
Thank you, sir.
Okay. I'll take this. Due to these mobile free electrons, metal possesses unique properties, characteristic properties, that is malleability, ductility. The property by which a substance can be spread like a sheet is malleability. Drawn into wires is ductility. That property is seen only with metals. You cannot take sodium chloride salt and draw it into a sheet or a wire. It's not possible. So thermal conductors and electrical conductors, that's because of free electron. They possess bright luster on the surface. Because of this lustrous nature, only some metals are considered as precious, like gold. And photoelectric effect, by the incident of radiation, they emit electrons because electrons are free. Thermionic emission. Upon heating, electrons start ejecting from the surface of metals. Free electron is the reason for that. High melting and boiling points. The nature of metals generally vary from being quite soft to very hard. Like S block elements are soft because they contribute less number of electron for metallic bond, whereas D block elements, the two tungsten molybdenum, are found very, very hard. So for the reason that they contribute more number of electrons for the formation of metal. So fine. So with this, we'll stop at this stage. Meet you in the next class with some more differences. Okay, right. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Right.
So can I go to the previous slide?
Yeah.
Thank you, sir.
Yeah.
Yes.